Okay, so welcome back everyone. This is part two. I didn't actually think we'll have a second part, but it looks like the content required us to obviously look into things a bit more in depth, which is what we will try and do now, at least from a simulation and me kind of showing you a little bit more in terms of the MATLAB equivalent of all the content that we've spoken about today. All right, so just a reminder again where we left off. So we were obviously trying to integrate all the various linear and rotational accelerations such that we can have the state variables quantified. And with that, we are able to have a complete model for us to simulate. All right, so what we will do now is we will now, before I do that, let's just talk about a bit about, because obviously some of you wanted to do that, but I have dedicated a completely different webinar just on drone simulation and planning, which is quite important, I think, to be dedicated on its own, and I've done the same for flight controller development. But let's just talk about a little bit before we get into the MATLAB. So this is an example of what we call a mission planner. And this particular one is actually called Mission Planner. It's free software you can download on the internet. It works with most drones, but usually the ones that run the ArduPilot code base. Now, what this Mission Planner is able to do, as you can see from the picture, is able to give you a sense of one, how to plan a mission, but also how to execute a mission. Because this mission plan has got very good functionality for radio communication, for parameter monitoring, for horizon monitoring, and also for fault finding. So you're able to send, via this mission planner, you're able to send fault finding instructions to the drone while it's flying to see whether its health and status is still as per what you were hoping it was. So it's a very interesting kind of piece of software. It's quite elaborate. As you can see, you're able to kind of do a lot of things and also plan your waypoints around, and then kind of hit this button here, connect, and then hit send, and it gets sent to your drone, and your drone's got all the parameters that it needs to do. And what we will do in the next kind of webinar, maybe in a 2 week or 3 weeks time, what we will do is we will now go into the simulation. Obviously, we will not use, we will give you some form of just kind of run through of mission planner. But what we will do, which is quite important, is we will create our own mission planner in a way, and we will design the guidance algorithm. We will design the waypoint tracking algorithms, and we will also see in 3D how your drone is performing depending on the different types of sensors it has. So we will simulate some of the sensors, and we will be able to get an understanding, because that's important from an engineering point of view, not just to click and play with the application, but to actually understand its fundamentals. So that's what we will do in the next tutorial or webinar, if I could put it that way, when it will just solely focus on drone simulation and will be an upgrade of the drone model that we obviously would have achieved and simulated today. So I think, and it's pretty straightforward. That is ultimately what its function is, and obviously it will give you a sense of comfort knowing that there is a program that is able to handle all your drone operations. Okay, now before I blow on, let's go into MATLAB, and then let's try and see what this drone model looks like. Okay. All right. So now we're in MATLAB. So you will recognize, hopefully, all the various pieces of code that was in the document is in the script. So basically, there is no need to kind of figure out, obviously, there are different parts, but usually it has followed a very chronological order. So there's no need to kind of wonder where everything is, but there is some extra, obviously, because it's MATLAB, and MATLAB doesn't know everything, and you need to tell it. different things like initializing your control, but you don't really need to, but it's a good practice. Initialize your control. As you can see, the physical properties were assigned here. I don't know if you know what this is. This is just to clear the axis of your plot without necessarily closing the plot, which is quite, you will see why. And then we talked about the force multiplier, this G factor in working out the controlled forces and moments. And this is, and it's quite important. It says this is required as it represents the motor and propeller, as I said. But it says that what we want is to be able to get 2 times more force when the throttle is at maximum, and maximum is 1. So the one thing I didn't speak about in the previous part of the tutorial was, you try and keep it to the throttle limits to 0 and 1. So at least it's manageable versus an arbitrary value. But then it means you have to have a very clear force multiplier to say, if it's 1, what I'm giving to my motors is full throttle that will give me twice its weight. That's what this is. It will give the force twice its weight. Okay, so basically 2 Gs. Okay, so we talked about that. So now what happens here is now we now go into a modeling and simulation framework. And we did speak about the time step, which is used for integration, but it's also used for simulation. So what this time step is basically saying, it's got a time step for 0.01 seconds, which is pretty small, but not that small if you really want to get into the finer, but it's good enough for this model. And then what we define is a time vector that basically goes from 0 to 20 seconds in that time step. Okay, so in terms of setting up a simulation, the only thing that's you need to do for the sake of this tutorial is set everything up in a for loop, because there is an integration and the previous value gets used in the next value, and what that actually means is it's just a for loop. That's what this is. So a simulation in many ways is just a very elaborate for loop of state variables. Okay, so just keep that in mind when you think simulation. And so we looked at, I'm not going to repeat, the linear acceleration now gets calculated, and then integration, all of that gets calculated. Then what happens here is, obviously we spoke about the control forces and moments gets calculated, the constraints gets inputted. So it's all set up, and the integration. So what this does is, if I can, which is quite nifty in MATLAB, this gets updated, gets used in the resistive moments. So all the one is your velocities, gets used in calculating drag and calculating resisting rotational drag. Then what these variables are then done is, when it goes back to the top of the loop, is to calculate the next linear acceleration such that it gets integrated here and the loop carries on. And that's it. And that's your equations of motion in a script fashion. Obviously, there is a way of doing this without scripting, but this is understanding fundamentals. There is something called Simulink that uses the very thing that I've just spoken of, slightly more elaborate, but ultimately by principle does exactly the same thing. Okay, so what now we can do with all this information is now we can simulate. But simulation requires you to see what this is. Okay, so it requires you to see and for you to understand. So what I've done is, you obviously have to set some initial and some intermediary conditions. So what I've said here is, I've said, okay, since this time, t is time, and I is the index in the for loop, just remember that, I is the index of the for loop. I say, what if time is greater than 0.5 seconds. So after 0.5 seconds, apply the throttle at 0.6. Remember, it's got a limit between 0 and 1. So 0.6 should ultimately elevate. Because remember, if it's 1, it's twice the weight. If it's half, it's exactly the weight. If it's slightly more, it elevates, but slow. So from 0.5 onwards, apply throttle. Okay, so this is basically me programming what I would have done if I had a remote control in my hands, and I will wait to apply throttle. Okay, quite important. Then what I'll do, step 2, is at 3 seconds, so obviously it's applying throttle. Because it's ideal condition, this drone will just not drift, will just kind of rise. And then at 3 seconds, reduce the throttle to 0.5, and then apply a pitch. Okay, apply a pitch command, and obviously a pitch command here. I didn't speak about this, but it's a bit complex, but it's not so complex. But I think I'll leave it up to you what it means, why a negative pitch command gives you a negative pitch angle. A positive pitch command gives you a negative pitch angle. There's a reason for that, but you will obviously have the script and you can go through it yourself. But so what this does in this step is that now it basically, I'm applying a different stick to say, pitch the drone so it can go forward. Okay, and we will see what happens here. What this does is, because this runs at 0.001, which is 100 hertz, you don't want to kind of plot every single point. You want to maybe plot a fifth of that, which is 20 hertz, and see what that does. Okay, so so this was the script. Let's see how we can simulate and see what does that look like. So what we will do is we will now display the altitude and the ground. Okay, altitude is your Q5 and Q6. So the 5th state and the 6th state, which is your position X and your position Z. Position X is your, forward, backward, right? And your position Z is up and down. And that's what we will be plotting. We will be plotting those states. You obviously can plot a lot more, but we will obviously look at that first. Okay. After this, what I'll do is I'll turn everyone's video on, so we can obviously interact once the video is done. But it's quite important for the sake of this tutorial to kind of understand the basics before you can obviously add complexity to this. Okay, all right, so let me go now to MATLAB itself. This was just the script editor, and then we will be able to, okay, so let me just clear this first. Okay, so what I'll do now is, and I already have, already done this, so obviously I've done this before. So what I'll do now is just run the script. Okay, so just down here, I'll run the script and you will see what happens. And I will try and obviously make it such that you can see it again and again. So what happens here is the drone now is rising, obviously gaining altitude, and then it's pitching. But then see what happens here. Because there is, now this is where you get to understand why there's a need for a flight controller or for an autopilot in a drone. Because a drone is inherently unstable. So unlike potentially an aircraft that will just, once you pitch it and you leave it alone, if it's stable, it will just keep flying like a glider and then kind of land. This drone basically just shoot it all the way back down again, all the way to the ground. So let me run it again so you can understand what happened. So remember, the axis is altitude and then ground, and all in meters. So this drone, goes all the way up to about 14 meters in altitude, and then it starts descending and descending quite fast. Let's try it again. Okay, so it's quite clear what happens here is during this phase, only the throttle was applied, hence the linear increase in altitude. And then somewhere in here, after 3 seconds, as you saw before, you apply a pitch command, and then the drone pitches. So a drone has to pitch in a negative, so because pitch angle is positive up this way. Pitch is negative, so the forces allows it to move forward. But then what happens is it also loses force against gravity. So that's really why you see a loss in altitude. So your gravity is always pulling down, but as soon as you tilt and you decrease throttle, you lose height. So second integral of velocity is height. Second integral of acceleration is height, and then you drop down quite fast along here. So if you were to change, let me change the time. So let me just go back so you guys can see what I'm doing. So if I were to now change, instead of the throttle going down to 0.5, I keep it slightly up at 0.55, and then let's see what this does. And hopefully you should see that it goes all the way up. Okay, so actually that's just too much. So that you can see it doesn't, because I didn't throttle down as much, it stayed in the altitude and kept increasing. So let's just, for the sake of the simulation, you guys can see, I will change it to 0.1 or 0.2, so at least it's easier to see. So as you can see now, it rises. Okay, so obviously it should kind of veer back down again, and it doesn't. Okay, so basically what I'm doing now is I'm applying a different throttle setting with my thumb, and so that the drone doesn't fall out of the sky. And that's exactly the job of an autopilot. Okay, so let me just apply again to 5.1. So for the sake of the simulation, and we can all see what that does. All right, so again, so it's a much more stable, as you can see. It still falls, but it doesn't fall all the way to the ground. Okay, so this was only a 10% more in terms of throttling back to the previous value. So instead of throttling back to half, I throttled back to 0.51, and this is the difference. Okay, now if I were to now say, so let's just do a different event. This is for the sake of you understanding. So you'll get the script. You can really kind of go wild with it and get an understanding. So now if I were to now say, okay, at 0.5 I do this, at 0.5 seconds I do this, at 0.3 seconds I do that. Now if I were to now say, we add a step 3, right? So step 3, bring the pitch angle to pitch command to 0. Okay, bring pitch command to 0. So, and we will maybe do it at after, I don't know, let's just say when TI is 6 seconds. You can always change it, but this is just for the sake of illustration. Let's say 6 seconds. And then what I want here is, I want this pitch angle to go back to 0. So, I want to bring the drone back, to 0, or in terms of command. Okay, so just because I commanded it doesn't mean it kind of kicks back to 0, because it's accelerating. And then what I want to do is I want to make it slightly hover. Okay, so this is a slight hover. Let's see what happens with this. I haven't done this before, so I actually don't know what will happen. Let's just see. Okay, so it pitches. All right. Okay, so this is now what happened here. What happened here is, now because the drone is hovering, or not the drone is hovering, actually it's not hovering, as you can see. I've just commanded it to 0, but I haven't commanded it to have a negative moment. So what it does, it's now the drone has gone back to this attitude, but it's still flying this velocity. Okay. But if I were to command it back to a negative angle, you will see that there will be a kick to your drone where it now wants to fly slightly more vertical. So let's just try that. Okay. Let's try that. Okay, you probably didn't see that. So let me run it again. I can see you didn't see that. So let me run that again, where you can see a difference in if you change your pitch angle to 0. And you can see that the drone doesn't fall anymore, but it now kind of translates in that in basically in a linear, not in a linear, in a steady state fashion. So this is a 0 acceleration, pretty much 0 acceleration, or very little because it's close to throttle. 0 acceleration, and it stays there. Now, if I were to now change it to say, instead of that, I want it to try and hover. Okay, to try and hover. I don't think it will hover, but let's just see. If it will hover, it's quite important for us to, and this is really just gets you to the feel for, before you design a controller, you get an understanding of how your plant behaves. So let's just run this again. So what happens here, it's now getting to a point where it's hovering. Okay, it's hovering, or at least it's maintaining altitude. So, you know, because what I haven't done is I haven't caused a negative moment to arrest the velocity, because, you know, your force, even if it does this, right? Even if it does this, the drone is still moving because there is no acceleration to, you know, cause the velocity to change direction. The only thing that it does is just it slows down because of drag. It slows down because of drag. So let's just do that again. But now change the pitch angle to be slightly negative, and then hopefully we'll see what happens. Okay. So let's change that. The script to be slightly negative. So we take this to slightly negative. Let's just do points, I don't know, 0.1. Okay. And then we should be able to see what that does. Okay, so what this has done, which is quite interesting, what this has done, it has completely slowed the drone down, because obviously before, you know, the drone kind of had a lot longer velocity, and then it has kicked in, it has allowed the throttle to remain at 50%, but hasn't really brought it back. So which is quite interesting, because what this is saying that for you to bring the drone back to hover, you have to not only control the angle at which you are pitching, but you also have to control the amount of throttle that you apply, and that is the job of the autopilot. Okay, now we will do one last thing before I end this video, and we go back to just doing the flight, just have an overview of flight controllers. We will do one last thing, which is we will now change what we call, so if you are able to now see the effects, there's quite a few parameters that you can play around with. For example, the mass, you can play around with the inertia, because those are physical parameters you can change. And this would be different drones, they have different masses, they have different inertias and different coefficient of friction or drag. And what you are able to do is you're able to now change the behavior of the drone in the environment. So for example, if I were to now change the gravity, for example, to let's just say 10, so maybe slightly heavier gravity, I don't know which planet that will be, but this is just for argument's sake, and that is the power of simulation before designing or building something, is now if I were to now try and do something like that, now the gravity, what it does is it clearly shows that not only has an effect, but if you have enough force, so you can still have gravity, but if you have enough force through it compensates for changes in gravity, and that's quite important. So if your gravity changes, obviously I didn't change it a lot, but if your gravity changes, it can be compensated through your forces. Okay, that's really something that I wanted to show in terms of that. Now, I think let's just go back to this is one last thing, really. I didn't want to make this video too long. This is one last thing that I wanted to show everyone in terms of just closing this tutorial off. Okay, so obviously we talked about Mission Planner. Now I just wanted to have a very quick overview on flight controllers. So flight control is quite a complex domain. And let me actually, I'm not showing, or am I showing? Okay, I am showing. All right. So flight control is quite a complex domain. Hold on. Am I showing this? Yes. Okay. I hope I'm showing this. Yes. Okay, great. So it's quite a complex domain. What I have here is an example of a microcontroller. Every flight control, so you can think of, any flight control, has what we call a microcontroller. And a microcontroller, and I've got one here. Let me just try and find it. A microcontroller, you guys can see this. This is called a TINSI. It's exactly the same in the picture, and I use this for my research. It's got the power of quite a few pins, and the whole idea with the pins is that it's got wiring that you can connect all sorts of motors, GPS, for location, IMUs for measuring rate, like we spoke about. So because that comes from a measurement to know what that is, or velocity. That is, again, a sensor that measures that. It's called a airspeed sensor. So then what this does is that it's got a computer inside, right here. It's got a computer inside, or a CPU, that then does computation on basically your autopilot commands and how you mix them and how you send the commands via what they call PWM, which is pulse width modulation. Basically, it's pulses on your motor, and the different shapes of pulses causes a different amount of force. And that's really what this does. Without this, you have to keep on adjusting as your pilot. You've got to keep on doing what I just did. Change here, and continuously. But if you have something like this, you're able to basically do a command, leave it alone, and the drone will be stable. Okay, this is what I wanted to show. There will be a completely different section on this, completely different tutorial where we'll be designing the autopilot. We will be analyzing the performance. Even though some of you haven't really done PIDs, we will try and kind of quantify what that is in layman or slightly less complex terms, and ultimately bring some form of completeness to the drone development and what it means, especially towards mass, towards different cheap sensors, towards different cheap actuators or propellers. Different propellers have different effects, and ultimately bring your flight control development to a closed loop. Okay, that is what I had for today. I hope all of you had some form of. I hope it wasn't too much, but obviously we'll get some feedback just now. And but to all of you who are watching either through the various social media um, platforms, thank you for watching. We will schedule another one maybe in a few weeks' time. Like I said, going in more depth in drone simulation specifically, and obviously flight controller development thereafter. Yeah, thanks again for watching. Until the next one. Cheers.